Up until now, I've kind of glossed over intermediate operations. For one thing, most aren't that complicated or difficult to understand. I've used filter, limit, map, and sorted in my examples. I also showed you a quick example of using distinct in the last challenge. As you can see from this table, the operations you've already seen briefly cover half of the basic operations available to your stream pipelines. I'll start by talking about the set of operations that may change the number of elements in the resulting stream. In this group, the first is the distinct operation, which removes any duplicate values. This operation depends on the stream type's equals method to determine the uniqueness of a stream element. Next, there is filter, which takes a conditional statement that evaluates to true or false, usually based on some attribute of the stream element. Elements that match an operation's predicate, meaning the condition returns true for that element, are kept in the outgoing stream for both the filter and take while operations. In contrast, elements will be dropped from the stream until or while the operation drop while's predicate is not true. You've already seen the limit operation in action. This defines the exact size of the stream, cutting off the stream elements when this size has been reached. This operation usually turns infinite streams into finite streams. The skip method allows you to skip a certain number of elements, meaning they won't be in the outgoing stream. Let's see what we can do with some of these in code. I've created a new project called Streams Intermediate and have the usual main class in dev.lpa. I'm going to start with the ABCs. I'll use int stream.iterate, casting the capital letter A to an integer value. This lets me do integer math easier on my stream. This also means my stream is made up of integer primitives. I'll use the 3-parameter version of iterate, so my second argument is a predicate lambda. I want to continue to produce integers for the stream until I get to the integer value of a lowercase z. To do this, I'll make this condition test that the value of I is less than or equal to whatever the integer value of lowercase z is. Finally, the last argument is a unary operator, and that's just going to increment each subsequent value by 1. I'm going to get integers representing any characters between uppercase A and lowercase z. I'll print that out using printf. I can pass an int to a character specifier, as I show here. Here is another example of a pipeline that has no intermediate operations. If I run this now, you can see I get a couple of characters that aren't alphabetical characters. I'll filter those out. The character wrapper provides a method called isAlphabetic that takes an integer and returns a boolean. So this is a perfect opportunity for a method reference. Running this gives us just the uppercase and lowercase alphabet now. Let's say that next I don't want any letters from A through E. This can be done with an additional filter. I can add the code to my first lambda expression, or I can include an additional filter operation, which is what I'll do here. In this case, I can use another method on the character wrapper class to uppercase that takes an integer and compares that to the literal E character. If the value is greater than E, it will be part of the output stream. There's really no limit to the number of intermediate operations you specify, and can use an operation many times and in any order you want. Again, these operations are a specification to the stream processor. The processor may decide it's more efficient to join those two conditions together in the black box of the stream process. This is why we have to stop thinking of these operations as methods, because in some cases they'll never be used in the way you define them, but will be optimized by the stream processing code. Let's see what happens when I run this. You can see I get the result I wanted regardless of the way the processor decided to get that work done. If I only wanted to skip the capital letters A through E, I could use the skip method. I'll comment out that second filter to show you that. Next I'll add skip as the second operation, skipping 5. Running this, you can see this operation did exactly that. It skipped the first 5 generated elements and the output starts with a capital F. You might ask why you'd do this, and this probably isn't a very good example, since I could just change my iterate method to do this. You'll definitely encounter situations though when you'll want to skip elements in a stream. There are 2 other methods that let you fine-tune what gets skipped or what gets included, take while and drop while. I'll comment out the skip 5 statement and instead include a drop while statement that will do the same thing. This operation takes a predicate and will filter out any elements while they match this condition. Unlike filter, this predicate is only evaluated for elements until it first becomes false. I'll explain what I mean by that in more detail in just a moment. Here, I'll drop any characters that are less than or equal to a capital letter E. If I run this, I get the same output as with skip 5, but this way gives you a lot more control. As I said, this will continue to exclude elements until this predicate turns false. I'll change my predicate to ignore case by making the character uppercase before I test it. Running this. The output didn't change. Did you expect the letters A through E in lowercase to be dropped? Well, that's where the word while in the operation name becomes important. This happens until the predicate becomes false the first time, and then that condition is no longer checked. Think of this as a mini while loop. It'll drop data until the condition becomes false, and then it moves past the loop altogether. Its job in the pipeline is complete and won't be revisited. If you combine this with a take while operation, you can effectively describe a range of elements you want. In this case, I'll take elements while they are less than a lowercase a. Running this, you can see I get letters F through Z in uppercase. The drop while and take while work well with ordered streams. If the stream isn't ordered, Oracle tells us the result will be non-deterministic, meaning the results may differ upon subsequent executions. Finally, there's the distinct operation. First, I'll comment out the drop while and take while operations. I'll use a simple map function to map all elements to an uppercase letter, then I'll insert the distinct operation after that. Again, this is probably not the most logical piece of code, but it does demonstrate how distinct works. I will run this and confirm I only get A to Z here. For another example, I'll generate some random letters instead. First, I'll print out a new line to separate the output. I'll set up a local variable random, a new instance of the random class. I'll create a stream source. I'm going to use stream this time instead of int_stream so that you can see I can use stream with integers somewhat seamlessly. Java will do all the auto-boxing and unboxing required. I'll execute stream.generate, which takes a supplier, so it has no arguments, but returns a value. In this case, I want to return the result of the random.nextInt method. I want to pass the characters, casting them to ints, so it's clearer that I'm focusing on character values. Since this is a random generator on an infinite stream, I'm going to set a limit of 50. Now I'll call distinct, I'll then sort my integers and print them out. I chose 50 to limit the stream, because I don't want to actually get a full set of characters each time. Using 50 as the limit means the probability of producing a nearly full alphabetical set is less than likely. I will run this a number of times. See how I got most of the letters when I use 50 as the limiting number. I won't usually get a full alphabet. If I remove distinct, I'll see every letter generated but in order. Running that. You can see the results without distinct. If these pipelines are starting to feel like database queries to you, that's for good reason. The Java API designers designed the stream to let you process data in a declarative way, much like a structured query language or SQL in a database. This lets you say what should happen and not actually how it will happen. If you've had experience querying databases, you might be familiar with the limit and distinct keywords available in many database query languages. The filter operation represents your where clause and sorted would be your order by clause and so on. When we get to terminal operations, you'll see there are aggregate functions commonly used in queries as well, such as max, min, count and so on. This feels like a good place to pause a moment, so I'll end this video here. In the next video, I'll continue the discussion with the second set of intermediate operations I want to talk about. These process all elements in the stream. See you in the next video.